Today my co-presenters are Elizabeth Wagner and Joan Lawler, both from WJE. And our topic for the presentation is field verification of service life models of existing structure. So to start with a little bit of background, why do we usually consider doing service life modeling for existing structure? We do this type of analysis to more effectively evaluate the remaining service life, and also to provide rational basis for repair decisions to extend the service life of the structure. And the best approach to predict the service life of an existing structure is by careful evaluation of its performance, past performance, and actual current conditions. And we do that through field investigation. And our typical approach consists of overall visual survey and sounding. And also we do scanning for reinforcement location and concrete cover using GPR or cover meters. And we do corrosion non-destructive evaluation to provide an indication of the corrosion risk and also identify location of active corrosion. And we use half-fill potential, corrosion rate measurements, concrete resistivity for that. And then we collect also material samples and perform laboratory testing. So after that, we feed all of this data into our service life modeling software. We use WJE, we use WJE Castle. It's a diffusion-based model that also considers convection zone near the service, where chloride transport is not necessarily governed by diffusion. Being developed in-house, WJE Castle offers us full control over the evaluation process to facilitate a customizable approach to the circumstances and the exposure conditions unique to each structure. It also can consider site-specific conditions, and this includes special cases, including sealers, coatings, use of corrosion-resistant reinforcement, presence or installation of overlays. Also can consider effect of cracking, and pre-existing chloride profiles, which we are going to present on in one of the project examples that Elizabeth is going to show us today. We have used WJE Castle in several projects, and also to consider the variability for the inherent in the concrete elements, we use a full probabilistic modeling approach, and that considers a statistical distribution of key parameters that we consider control the corrosion process. So we have used that for existing and new structures, including transportation, power generation, industrial and government buildings. So as I mentioned, the inputs are derived from the condition assessment findings that we measure directly from the existing structure. And these input data include exposure and concrete parameters, concrete properties parameters. And we collect this information based on testing of the concrete cores and the chloride profiles. And also other inputs is the cover, and this we use a specific distribution of the data that we collected from the structure. And chloride threshold, which is dependent on the type of reinforcement, also based on the mixed design that we learn about usually from the petrographic examination of the core, or also we validate it based on the bar condition of that we do based on visual inspection of the bars, whether it's collected in the cores or through an inspection opening. And the output of our analysis would be the percentage of corrosion-related damage with time. And based on the damage threshold or the service life criterion, we can estimate the remaining service life. And then we validate our results based on percentage of damage at current age that we estimate based on the field investigation. And we did benchmarking and validation of our approach through different projects, including cooling tower, marine structure, structures, and these projects included use of plaque bars, galvanized, and epoxy-coated bars. And we continue to validate our model on ongoing projects. And today we're going to focus on 2 project examples where we performed benchmarking and validation. So our first project example here is Barber's Cut Terminal at Port of Houston. So it's Barber's Cut Terminal. It's located at the Galveston Bay off of Gulf of Mexico. So the water there is brackish water. Its salinity was about 1/3 of the salinity of typical seawater. So there is plenty of chloride to cause corrosion risk of the reinforced concrete elements there. We did our investigation after 40 years of the structure being in service. And at that time, the structure was scheduled for rehabilitation to attain additional 50 years of service life. And this rehabilitation also included upgrading the structure to support new, bigger size cranes. So it included adding also new elements, including drill shafts and some girders and portion of the deck. So the objective of our investigation was to characterize the current condition of the existing structure to provide basis for the repair recommendation. And to do that, we followed the same approach I mentioned earlier for field investigation, where we started with element level visual inspection of all accessible elements, and then we selected representative study areas for in-depth assessment, including cover measurement, corrosion NDE, and collecting material samples. So here I'm showing an example of some of the results collected at one of the study areas on one of the drill shafts. So here's the half-cell potential results and also the location of the cores that we collected. So we made sure to collect cores at different heights to capture different exposure conditions. So based on the test results we conducted during our investigation, we defined the different exposure zones. So we have soil, submerged, tidal, splash, and atmospheric zones. And based on our results, we found strong correlation between the estimated surface chloride concentration and the corresponding height above mean low water level at which the cores were drilled. So on the right here, I'm showing the figure of the surface chloride concentration estimated for the different cores. And showing with the height above the mean low water, so with the different exposure zones. And we use this correlation for our modeling. So we use the power model fit for the surface chloride concentration with height. And to capture the variability of the surface chloride at a given height, we calculated the prediction interval, and we used normal distribution at each height based on the prediction interval limits. So then we used WJE Castle to perform our service life modeling. And here I'm showing the results for a couple of the elements in the structure, bulkhead beam and drill shaft. So for the bulkhead beam, for example, we had enough information from the field investigation about the percentage of damage on each of the 3 beam faces, the underside, vertical, and top side. So we modeled those separately over the next 50 years, which puts us at an age of 90 years. And as you can see, the damage is expected to increase on all surfaces with time. And the model actually showed close correlation to the amount of damage that we observed in the field, which verified our modeling results. And based on the results, we identified high risk for corrosion future deterioration, and we recommended preventive repairs that's needed for all the surfaces. And similar approach we use for the drill shaft, where we verified our model using our field investigation results. And we found also a good correlation between the percentage of damage predicted using our model and also the percentage of damage from our field investigation. And based on the service life modeling results, we recommended preventive repairs needed in the tidal zone to achieve the additional 50 years of service life. And we used all the information we gathered from our investigation at the existing structure to inform the durability design of the new structure. So the correlation was for the surface chloride concentrations, we used that along with what we learned about the propagation time for the different exposure zones to run service life modeling, considering different alternatives for concrete mix parameters, reinforcing material, and concrete cover thickness to achieve 50 years of design service life. And based on that, we recommended concrete mix design parameters that were summarized in a corrosion protection plan or reflected in drawings and specifications. And with that, I'm going to give control to Elizabeth to present our next project example.
Thank you, Marwa. I'm going to turn the attention now to another project example, which is the Interstate 480 Bridge Piers in Omaha, Nebraska. The I-480 is a roughly 1.5 mile long overpass system in downtown Omaha. The bridge piers themselves were constructed around 1970. And after about 30 years in service, there was a condition assessment performed by others on behalf of the Nebraska Department of Transportation in 1997 that looked at the condition of the bridge piers and made recommendations for their repair and maintenance. So this condition assessment included things like chloride sampling, delamination surveys, and crack surveys. And based on the findings, the party that performed that assessment recommended a series of rehabilitation activities between 1998 and 1999. And this included replacement of all of the joints and drainage systems on the entire length of the bridge section in this area, as well as surface repairs of 61 of the piers and electrochemical chloride extraction treatment, or ECE treatment, of 26 of the piers. So what ECE treatment is a surface treatment that's applied to concrete structures where an electrical field is applied between the reinforcing steel and a temporary surface mounted electrode on the surface of the element. This electrical field pushes the chlorides from the reinforcing steel back out of the concrete and into this temporary surface anode, which is then removed after the treatment, taking all of these chlorides out of the concrete with it. As an additional byproduct of this process, there's also hydroxyl ion generation at the reinforcing steel, which can help to repassivate the steel that has already initiated corrosion. WJE went out to these bridge piers in 2018, about 30 years after the initial, the major rehabilitation effort, or rather 20 years after the major rehabilitation effort. And our purpose was to perform a condition assessment and service life model of the piers. We looked at specifically 18 of them, 14 which had been treated with ECE and 4 which had not. And our objectives were to assess the current condition of these piers, predict the remaining service life so that we could help inform repair decisions, and then also evaluate the effectiveness of the ECE treatments. Like Marwa showed in her previous slides, our field evaluation included a combination of visual and delamination surveys, GPR cover surveys, core sampling, and corrosion rate measurements. Our findings showed that there were various levels of distress currently present at the bridge piers. This is an example of one of the more severe cases of deterioration. You can see in the figure on the left that there were a number of delaminations that were occurring in areas that had been previously repaired in the 1990s, which suggests that the same root causes of the failing of the joints and also failing of the drainage system were causing a lot of the corrosion-related activity and chloride exposures we were seeing. So based on our field observations, we grouped the piers into two categories. One of the categories was primarily piers that were located at expansion joints, which we considered to have a high exposure to chlorides. These were typically characterized by moisture staining, corrosion staining, some efflorescence on the surface, and in some cases, peeling away of the surface coatings. Other areas which were primarily away from the expansion joints we identified as low exposures. We took a total of 36 concrete core samples from these areas and divided them into high exposure and low exposure categories. Using the chloride profiles that we obtained from each of these cores, we fitted diffusion coefficients and surface chloride estimations to these cores to get an estimate of what the concrete's diffusion characteristics are and also what the average exposure conditions are in these two areas. We also performed a service life model looking at these two exposure classes, the high exposure and the low exposure. But our models also considered what was the effect of the ECE treatment itself. So if I'm going to show an example of what the chloride profile might look like in one of these higher exposure areas. So initially we have no chlorides present, but over time, 10, 20 years, and all the way up through 1999, these chlorides are starting to build and diffuse through the concrete. Once the ECE treatment is applied, we consider there to be a reduction in the chloride concentration. We assumed an average of about 60 to 70% reduction based on the measurements that were performed by the party that had performed the ECE treatment in 1999. And then this modified chloride profile is then progressed forward in time so that we could obtain estimates of what the current chloride profiles are and compare those to our models, if that works. So we had a couple cases that we benchmarked with our models. The first is the 1997 field investigation. There were powder samples drilled from the piers, and chloride concentrations were measured at depths between 0 and 1 inch and 2 and 3 inches. So we looked at our models' estimates of what the chloride profiles would have looked like in 1997 and compared those to what were actually what were measured on the piers. And we found that our predictions were within about 10% of the measured values on average, which gave us good confidence in our model. Additionally, when we looked at the amount of damage that was predicted in both the cases of high and low exposure, in cases with ECE and repairs, and in cases where there were untreated piers, we compared that to the observed damage that was documented in the 1997 inspection and also in our 2018 inspection, and again found very good correlation between the observations of both studies and what our model was predicting. So based on our model findings, we were able to estimate that the rehabilitation, which included the ECE and joint repairs, extended the service life by about 30 years. However, we also found that moving forward in time, there was a high likelihood that we would exceed damage fractions of 20 or even 30% on these piers, and that they wouldn't necessarily reach the intended additional 30 years of service life. So we recommended to the DOT that they perform repairs of all of the expansion joints and drains to help limit some of those chloride exposures. We recommended repair of cracked and spalled concrete in those particularly distressed areas of the piers. And in the piers that were distressed and located at expansion joints, we also recommended additional corrosion mitigation. So to summarize, our service life modeling was performed with WJE Castle software, which offers us a customizable approach that we can use to consider site-specific conditions, such as the variation in chloride exposure like Marwa presented for marine structures, or the application of ECE treatment like I've just presented. Our model has been verified against field observations for a variety of structures and agrees well with the amount of damage and chloride profiles we've observed in marine structures, bridge piers, and bridge decks.